Hello everyone, welcome to AP Chemistry episode 1. Today we're going to be talking about moles. Now before we get to the number that moles are related to, let's talk about a more familiar subject. So let's look at the word dozen. So I think we can all agree by now that a dozen is equal to 12, unless you're talking about a baker's dozen. But let's talk about a standard dozen for now. There's going to be 12 objects, commonly eggs, could be something else, but it's a way of grouping things, right? So instead of saying, say, 96 eggs or some other outrageous number of eggs, you can call it, this would be 8 dozen, right? And this works similarly for atoms and molecules. So even a small, tiny sample of a substance often has way too many atoms to be able to count. So instead of saying something outrageous like 10 to the 23 atoms, you can condense it into 0.17 mole. And just like how a dozen is always 12, the number of atoms or molecules in a mole is always constant. That number is called Avogadro's number. So Avogadro is spelled like that. And his number is equal to 6.022 times 10 to the 23. Now that feels oddly specific, and that's because it is. The reason why this number was chosen is because if you choose any element on the periodic table, any of them, and choose some random element's mass number, so let's zoom into helium, you can see that helium has a mass number of 4. If you have 4 grams of helium, that is exactly this many molecules, or rather atoms of helium. So this this number was specifically designed so that the AMU of a molecule can correlate directly to the mass of 1 gram that is also equal to 1 mole. To find the molar mass of an object, it's accordingly very simple. So let's do something like water. So water, as we know, is H2O. And to do that, we just need to add the molecular mass of hydrogen. So hydrogen is 1.0078. Now since there's 2 hydrogens, we have to multiply that by 2. And then we just need to add the mass of oxygen, which is 15.999. Now if you add that up and bring out a calculator, 15.999 plus 1.0078 times 2 is equal to 18.0146. So this many grams of water is 1 mole of water. That's why we can also give the unit 18.0146 grams per mole. Now, because of this implies that every mole of molecule is a different weight. And that makes sense. Some molecules are bigger and more massive than others. And this is very well demonstrated by 2 common chemicals. So here's just water. This is salt. So we found water's molar mass. And what I want you guys to do is I want you guys to look at the periodic table. You can also look one up and find the molar mass of salt. So salt is a pretty common chemical. It's NaCl, sodium chloride. And the procedure goes exactly the same as usual. So you get the mass of sodium, which on the periodic table is 22.99. Since we have to conserve SFs, I will be just using that. And then we just add the atomic mass of chlorine, which is 35.446. And what we're ending up with is 22.990 plus 35.446. That's 58.436 grams per mole. Now to convert moles to mass or vice versa, all you need to do is multiply or divide by the appropriate molar mass. So both of these samples are 3.75 grams of each substance. So let's calculate how many moles are in each. So we have 3.75 grams of water. This is 3 sig figs. My scale can't go farther than that. And then since we're converting grams to moles, we have to divide by 8 15.0146 gram per mole. This means that the mole comes up to the top, gram goes to the bottom, grams cancel, and we can find the moles. If we do that, we get the answer of, let's see, we get 0.02816 moles. Because of stick figures, we have to round to 0.208 moles of water. Now I want you guys to figure out how many moles of salt is in this vial. That vial also has 3.75 grams of salt. So this is exactly the same procedure. 3.75 grams divided by the molar mass. Again, grams cancel, and we can effectively find the moles. So 3.75 divided by 58.436, that's only 0.064 moles of sodium chloride. So as you can see, even though these two vials have the same mass of substance, they don't necessarily have the same amount of moles of substance. But then we have another question. You know how we found the molar mass of a substance with the atomic mass here? So then how do you get one specific number for atomic mass? After all, most elements have multiple isotopes, so which one are we going to use? The short answer is literally every single one of them that has any significant amount of occurrence. So let me give you one example. So we have, let's say, boron. So boron has two major isotopes. We have boron 10, which has a mass of, 10, and boron 11, which has a mass of 11. So boron 10 is about 20% or 1/5 of all boron, and boron 11 constitutes the rest. The way you do this is simply by multiplying the mass number by the relative abundance. So if we multiply that, we get 2. Multiply these two, we get 8.8. And then we just add them up, we get 10.8. And as you can see on the actual periodic table, you can see that boron has a standard atomic mass of 10.8. This is how we find every other element on the periodic table as well. So now I want you guys to do one example problem. Let's do it with, say, chlorine. Let me bring up another sheet of paper. So chlorine also has two different isotopes, so chlorine 35 and chlorine 37. So chlorine 35 is 75% of all chlorine, the rest is chlorine 37. Now I want you guys to find the standard atomic mass of chlorine without looking at the periodic table. That's cheating. Alright, if you did this correctly, you should multiply these two together and these two together. So if we do that, 35 times 0.75 plus 37 times 0.25, we get 35.5 as the atomic mass for chlorine. Now if you look here, you can see that we're kind of close, 35.45, not bad. If we use more precise values, we would have gotten a better answer. So now what can we do with the mole? Well, there's a lot of things we can do with the mole, which includes making our calculations much easier. But for this unit, let's talk about the percent or the mass percent of each atom in a molecule. So let's start with something simple. Let's start with, say, carbon dioxide. So for carbon dioxide, you can see we have 1 carbon and 2 oxygens. Now, at first glance, it looks like oxygen takes up 2/3 of the mass and carbon is only 1/3. But that's not how it works, because you're basically comparing a basketball to a soccer ball. A basketball is definitely heavier than a soccer ball, in my very little experience in athletics. So this is actually going to be slightly different mass-wise. The way you do this is first you get the molar mass of carbon, or whichever element you want, and then you multiply it by the number of carbons in the molecule. There's only 1 here, so multiply that by 1, and then you divide that by the total molar mass, which is the sum of all the molar masses. If you do all the math, you can get 44.01, which lands you with the answer that carbon dioxide is actually only 27.3% carbon. Technically, I should put 27.29, but so you can see, even though carbon dioxide is only 1/3 carbon, it's actually less for the mass percentage because one atom of carbon weighs less than one atom of oxygen. So let's do one practice problem. Try finding the mass percentage for, how about, let's see, how about magnesium fluoride? Let's start simple here. So magnesium fluoride has the same procedure. So let's start with fluorine this time. So fluorine has a standard atomic mass of 19.00. Now since there's two fluorines, we have to multiply by 2. And now we get the same thing, 2 times 19.00, and the mass of magnesium, so 24.31. That means that the mass percentage of fluorine is 2 times 19 is 38. 38 plus 24.31. Oops. So that means that magnesium fluoride is actually 60.99% fluorine, even though fluorine is actually 67% of the whole atoms of magnesium fluoride. Now, because magnesium is the only other atom, you could subtract 100 from this. But if there's more atoms, you can just do the same procedure with, as we did before. Don't put the 2. There's only one atom of magnesium here. And then you should end up with, where was I? 39.01% magnesium. So that's unit 1 for, so that's the concept of moles. Thanks for watching. See you guys next time.